Thank you, Kenji. So yes, this is joint work with Thomas Kragh. Let me just remind people of the Arnold conjecture. Which says that Q is closed exact. And L inside the cotangent bundle of Q is closed exact Lagrangian. Then L is Hamiltonian isotopic to the zero section. Pardon? I'm sorry. Closed manifold. Thank you. So this is, of course, called the nearby Lagrangian conjecture, because if you take Q as a Lagrangian in any symplectic manifold, then a neighborhood is modeled after the cotangent bundle, and this says that if you take any other Lagrangian in that cotangent bundle which is also closed and which satisfy this exactness condition, then you can isotope it via Hamiltonians to the zero section. And we basically have no evidence for this, other than the examples of S1, S2, and S1 and S2. I think for the two torus we can do it if you drop the Hamiltonian assumption. So instead, what we've been doing all these years is try to prove some much, much weaker versions of this. So this is summarized by the following results of Kaya, Seidel-Smith, Nadler, Self, and Kragh, which says that under these assumptions, the inclusion, or rather the projection from L to Q, so L is contained in T star Q, and this projects, is a homotopy equivalence. So the proof of this fact used quite a lot of machinery, quite a lot of development in understanding Fukaya categories, but I just want to advertise that recently Kragh has found, I don't want to say an elementary proof, but found a proof which does not use the full, does not require using the word A infinity category. Okay? It just uses some kind of careful understanding of spectral sequence. Oh, actually, so in fact, the proof in this version will use some stuff that I will talk about, plus some additional ideas that he has.
Can I still use homotopy?
It uses quite a bit of holomorphic. I mean, you have to use Floer multiplication and kind of lots of discussions of homotopy and action arguments.
Doesn't use the word action.
Pardon?
The categorical proof doesn't use the word action.
The categorical proof doesn't use the word action. That's fine. I thought this audience would appreciate action more than. So, yes, well. Okay. So this talk is about improving the statement. Yes, thank you. Thank you. No. So Guillaume has a proof. He probably has to assume some Maslov assumptions still, because otherwise his sheaves would be, pardon?
I have invented a new version.
Okay, the original, okay. But
The original one
has a proof using okay, this is going to make the audience even happier. Microlocal sheaf theoretic methods. Yes. So, so this talk is about trying to improve this, and of course, it would be very nice if we could prove at least something like that they are homeomorphic. That's somehow maybe a long-term goal. But so today's result says that L cross 0, 1 to the infinity is homeomorphic to Q cross. Okay, this is slight abuse of notation. This is, should think of it as basically the Hilbert cube. So in some sense, you can imagine that it says that these manifolds are stably homeomorphic if you allow stabilization by things which are infinitely large. Now, this is not the way, of course, we prove it. We don't take a product with the Hilbert cube and show that they're homeomorphic. Rather, we just use the fact, so this is equivalent to L and Q being simply homotopy equivalent. And what I want to do is, well, so then you could hence you could have defined it that way, but there is a completely algebraic characterization of what it means to be simply homotopy equivalent. So this is also equivalent to the vanishing of the Whitehead torsion of the map F. Okay, and so what I will do first is define the Whitehead torsion of a map, and then we'll go back to doing some Floer theory. Okay. So what is Whitehead torsion?
Did you define F as the map from L to Q?
I'm sorry. Yes, I should have listed that by now. So what is Whitehead torsion? Well, let's fix a group which we will think of as being discrete, which will, in the end, will be the fundamental group of L and Q. By the way, we already know the fundamental groups are the same because we know it's a homotopy equivalence. And let's consider R, which is going to be the group ring of G. And we're going to study chain complexes over this group ring. So we consider pairs C, B, where C is a chain complex over R, and B is a basis. Okay. So when I get to it, the chain complex over R will be some kind of Floer group, and the basis will be the usual basis by intersections. Actually, since I've managed to do that. Okay. And what we want to do is consider, well, you could take isomorphism classes of such things. But we want to consider them modulo some slightly non-trivial equivalent relation. So mod out by following equivalence relations. So first you can change bases by any basis element. Let me just make sure. Any basis element by multiplication with plus or minus little g, where g is an element of the group. 2, you can apply an upper triangular change of basis with ones along the diagonal. Okay. And 3, you consider 2 such pairs to be equivalent if, so allow adding a summand of the form R goes to R by the identity, where this is equipped with the obvious basis 1 and 1. So if I perform any of the operations, I consider my corresponding acyclic. Did I say acyclic? No. So if we assume, so the collection of acyclic trivial homology complexes with bases modulo these relations form the Whitehead group. So it's called WH of G. Okay, that's all we need. Okay, so just some justification for these changes of these kind of operations that you're allowed to do. So the intuition should come from Morse theory. So say we have M to R, I'll just use F, a Morse function. And instead of doing Morse theory on M itself, we can consider the lift F tilde to M tilde R to the universal cover. Now the Morse complex of F tilde, this is of course naturally a pi 1 M module. Okay? And it's not acyclic, so I would have to, I'm not going to try to justify that right now, but so technically you're not going to get torsion out of this, but these 3 operations, they have a very kind of clear meaning when it comes to Morse theory. So one corresponds to just saying that, if you want to choose, and in fact, naturally a free pi 1 M module. If you want to choose a basis for this free pi for this module, you have to choose a lift, okay? And there is no preferred lift, and they of every critical point down here, and there's no preferred lift, and they differ by multiplication by G. Of course, the plus or minus is saying that when you do orientations in Morse theory, there's no canonical generator of them associated to a critical point. It's only canonical up to plus or minus 1. So this is choice of lift of critical point in M. 2, well, I unfortunately made the decision of writing it in terms of this kind of upper triangular change of matrix, but really it comes down to expressing it in terms of elementary transformations. Okay? And so 2 is the kind of operation, so this is operation appears when when considering a family of Morse functions. So I'm just saying, in continuation maps, so you have kind of a flow line from one critical point of index I to an critical point of index I plus 1. That's what you're counting usually in Morse theory. But it could happen that in a family, let's call this X, let's call this Y. It could happen that in a family, there is an exceptional guy that goes from X to X prime, both of which have index I, and then it continues I plus 1. And then the count of these of these exceptional solutions defines the change of coordinates that you need to do to identify the two complexes, and it's exactly of this form. They have this kind of upper triangular basis. Okay? And 3 is the birth-death phenomenon. Okay? You can just create two canceling critical points out of nowhere. Yes?
I mean, I'm just querying the use of continuation maps.
Maybe I shouldn't say continuation maps. Homotopy methods. Thank you. Homotopy method. Proof of invariance. So that's the Morse-theoretic version. But you can do a similar construction. So we can, well, anyway, so let me just keep going. So what is the Whitehead torsion? So now I should introduce the Whitehead torsion. Of a map. Okay. And I will call this like the classical notion of torsion. Well, let's consider, so let's approximate this by a cellular map. And here I'm basically using the fact that these are smooth manifolds, so they basically can be made into PL manifolds. Triangulate. So then F induces a lower star, and here I should say maybe tilde, but okay, gives me a map from the chains, my cellular chains, on the universal cover of L to the chains on the universal cover of Q. Okay, and this map is an isomorphism. Induces an isomorphism on homology. So you can take the cone of this map, and that's acyclic. So the cone, which is basically going to be the direct sum of the chains on Q tilde with the chains on L tilde shifted by 1, equipped with the differential, which is basically differential, 0, and F lower star, is an acyclic complex. Well, you could say the starting assumption is the map. If I really wanted to say the starting assumption is the map induces an isomorphism on homology. But if it's homotopy equivalence in particular, yes, not every map will have such a torsion. It needs to induce an isomorphism on homology. Okay. Cyclic complex, and therefore with a preferred cellular basis. So preferred basis coming from the fact that I take some kind of triangulation. And so therefore, we get an element, class of F, in the Whitehead group of the fundamental group of either of these spaces. Let me just call it Q because that's the Whitehead torsion of this map. And you have to do some work. One of the things one can do, and we will use it later, is the fact that I kind of gave him some motivation using Morse theory. Then I said, well, how is it defined? Classically, it was first defined using cellular approximation, using PL techniques. But you can also compute it using Morse theory. And maybe at the very end of the talk that will show up again. So this is invariant. And can be computed, can be defined Morse theoretically. Okay, so what is the role of Whitehead torsion in Floer theory? I think I have Michael here. So yeah, he thought about that, but maybe 15 or so years ago. But in the specific context that we're talking about, probably the closest earlier work is the work of Michael Sullivan. I think this was his thesis, who showed the following thing. So you assume that L inside M has, so this is, M is some symplectic manifold, satisfies the property that the Floer homology of L with coefficients in the group ring of L is 0. Then the Whitehead torsion of this Floer complex is well defined. And is invariant under Hamiltonian isotopies. So maybe a little bit of clarification would help in please explaining the meaning of what I mean by this Floer homology with coefficients in z pi 1L. So the easiest way to do it is to basically use this so that this thing is well defined. I mean, I think he did state it in the exact case, but it doesn't make a difference. I mean, but you have to make sure things are well defined. If you're in a setting where it's well defined, then. But I mean, it can't be exact because I assume that the Floer complex is 0. So the main thing is make sure it's well defined. So first of all, when I write HF star of L, what I really mean is HF star of L with itself. Okay? And if in addition we put in these coefficients, I don't mean that you just take Floer cohomology with Z and then tensor with this ring. What we mean is that whenever you encounter some holomorphic disk, for example, in the picture that Biran and Cornea like to use, you encounter some holomorphic disk that contributes to the differential. Sorry, this is a horrible picture. I don't quite know how to make it better. So just let's undo this part. This is some disk. Okay. So you imagine defining this as define Floer complex as the direct sum over all critical points of some function. I keep using f for everything, but that's okay. Of some symbol called x times the group ring. Okay. If I didn't have this guy here, then what we would do is we would just count the number of first gradient trajectories, and then we would correct the number of gradient trajectories by some count of gradient trajectories passing through some holomorphic disk with boundary on L. But if I have this, then every single time I encounter such a thing, what I want to do is I want to keep track of the homotopy class of the path that I get by running around the boundary. So keep track of the homotopy class. Oops. And when we say that it's invariant under Hamiltonian isotopies, you mean that you can actually extend this definition to HF star of L phi t of L, coefficient in z pi 1. Now this, by some invariance of Floer theory, will also have vanishing Floer homology, and his result is that the torsion associated to the pair is invariant. And this was a useful, I mean, this was kind of a useful result because it says that in some situations Floer homology vanishes, so you can't prove a non-displaceability result that way. But of course, if the torsion vanishes, yes, but about 5 to 10 years earlier. So, yeah, so I think in this context, this might be the right reference. Okay. So now what is it that we do? Okay. So the first part is some generalization of this picture where instead of having one Lagrangian, you have two Lagrangians. So what's one way of getting something acyclic? You just start with some Floer theory and you have vanishing homology, okay? Vanishing Floer homology. Another way of getting something acyclic is to get two chain complexes and a map between them, which is a quasi-isomorphism. So this is kind of a standard definition from Floer-theoretic literature. So L and Q, let's say, are Lagrangians, just to make people not complain about it, exact Lagrangians in a symplectic manifold. Then we say that L, that they are Floer theoretically equivalent. If you can find classes, let's call them U and V, in the Floer cohomology groups. I'm going to make my Floer cohomology groups now over Z. So you take the Floer cohomology from L to Q, and you take the Floer cohomology from Q to L. Okay, and you have an element here, an element here, such that the products U dot V, well, okay, let's do the multiplication the way normal people do it. This lives in the Floer cohomology of L with itself. So we assume that this is equal to the unit, and V dot U, the unit of L. V dot U is also equal to the unit of Q. So, of course, the main example that we can actually construct are L, cases where L and Q are Hamiltonian isotopic. And there are some examples where they are not Hamiltonian isotopic, especially if you allow non-trivial local systems, but it would be good to have more. Okay. So what I want to point out is that so these assumptions, so okay, if L and Q are connected, which isn't, so these assumptions imply that the following maps are isomorphism. So you can go HF LL, multiply by F, by U, sorry, I called it U. Okay, I have to think where U lands. HF LQ, multiply by V to HF QQ. These maps are isomorphisms and vice versa for swapping the roles of U and V. Just 1 second. Yeah. So are all isomorphisms. And also for swapping U and V. Now, if you're in an exact situation, these two groups in degree 0, I mean, these are isomorphisms in preserving gratings. If you're in exact situations in degree 0, there's only basically Z in here, only Z in here. So that implies that U and V are uniquely defined up to sign if they exist. There's essentially no ambiguity in their definition. Okay. So I think you can guess what I'm about to say next, which is that, oops. The first basic result, I mean, in the end, none of these results end up being that hard to prove, but so if L, Q in M are Floer-theoretically equivalent, then the map CF star of L, okay, let me just put it with itself, coefficients in Z pi 1m, to CF star L, QQ, coefficients in Z pi 1m, is a quasi-isomorphism, and its torsion is independent of Hamiltonian isotopies. So this sorry, here? No, this was an assumption. If you have something with Floer theory 0, then you can define torsion. I'm saying if you have an isomorphism of Floer cohomology, you can also define the torsion. Yeah. That's why I wanted to do this presentation with like 2 different examples. Floer-theoretic one with Michael, and then. Now this is actually a classical object. This is just, again, under the exactness assumption. This is just, actually, if you, well, it doesn't matter. This is just the cochains of L with coefficients in Z pi 1m. And this is thought of as a Z pi 1L module via inclusion. That's what. Okay, and the proof is, actually, we could use Sullivan's proof, but Michael Sullivan wasn't working in the exact situation, so he had to use some delicate bifurcation analysis to prove these results. And it turned out that if you're in the exact situation, you can use action filtrations, another thing that apparently Ivan doesn't like. So the proof of this ends up being much shorter than the proof of that result. Great. So now we apply this to our situation. So now we consider M is going to be a cotangent bundle. Q is the 0 section. And L is some closed exact Lagrangian. And we know, I didn't actually say this, when I said, the results of Sky, Seidel-Smith, Nadler, Sof and Kragh. So we actually know that L and Q are Floer-theoretically equivalent. So that means that there is a well-defined torsion, and if you actually look at it, as I said, in this case, in the general case, you have to work with fundamental group in the whole space, but in this case, so we obtain a map from the cochains on L with coefficients in just pi1 of L to the cochains on Q, coefficients in Z pi 1. Okay, Q and L are the same. So they have the same homotopy group, so I'll just do that. Same one, which is acyclic. And has well-defined torsion, has invariant torsion. But there is another such map. So this one coming from Floer theory. Okay. So we have two tasks ahead. One is show that this agrees with the classical torsion. And two, compute it and show that it's 0. I mean, the proof that it vanishes is not going to use the fact that it's classical torsion. It's going to use Floer-theoretic techniques. So I think I will start with the second part. So I'll first explain why the torsion vanishes. Just need a second to see where I am in my notes. Okay, so when I said that it's invariant under Hamiltonian isotopies, what it means is, so invariance says that the torsion of the map above agrees with torsion of a map, the map CF star L prime CF star Q prime whenever L and L prime are Hamiltonian isotopic. And similarly for Q and Q prime. So what we're going to do is use clever choice of Hamiltonian isotopy. It's easy to say that it's a clever choice because it wasn't due to us. It was first considered by Fukaya, Seidel, and Smith in some order that I don't know about because it didn't make it to their paper, at least not in a form that most people can recognize. So this choice of isotopy is based on, so to define the isotopy, you pick a Morse function let's call it big F on Q. Okay. Now this Morse function of course has the differential, and the graph of the differential you can write the graph of the differential like this. It's maybe not the nicest notation in the world, but it has pretty good meaning. So this is the graph of differential. T times df. T is some parameter. And you can do the same thing to L. That is, you can just, at every point, you can just fiber-wise add, to take addition and move every point of L by T times this. And because L was exact, and this is actually, this comes from an exact isotopy of the whole space, that the resulting Lagrangian, the resulting isotopy is a Hamiltonian isotopy. And L prime equals, again, so there's L plus T times df be image of L under fiberwise addition. So now, oh, there's chalk, great. So here's the picture that you should have in mind. So this is my cotangent bundle. And this is my zero section. Okay? And for some reason, I decide ahead of time to zoom in really, really, really far away so that L is just something hiding over here. I don't really know what's going on, but something hiding over here. Okay. Now, my T times df is going to be really, really, really large. Okay. This is Q plus TDF. And well, you know, since L was very close to the zero section from this kind of very far away perspective, there's nothing that can happen other than for L plus TDF to look like this. Okay. So what does this mean? This means that if you consider the action filtration on the Floer complex of L and L prime. So the action filtration on CF star L plus TDF. Let me not put in local coefficient systems right now. Breaks up into sub-filtered pieces. Well, let me just call it, just say, gives associated graded pieces. Labeled by the critical points of the function f. Okay? What do I mean by that? What I mean by that is that, you know, for some reason I insist on having different colors. So, different colors. Let's go over here. Okay? There's some intersection points of L and this image under this isotopy, which lie in this region. And first of all intersection points lie in an appropriate sense in the neighborhood of one of the critical points. Okay? And moreover, now there could be many, many different critical points here, and they could have different actions and so on and so forth. But from this zoomed out point of view, their actions are very close to the value of f. Okay? Actions of intersection points concentrate near the values of f. Okay, so to make your life easier, you should probably choose this Morse function to have so that all the critical points have different values. So why is this useful? Well, the action filtration on the Floer complex of Q with the image of Q with this graph also has this property, that its action filtration is labeled by the pieces of F. And so a very basic action energy, well, actually basically a very basic action estimate says that with so the map CF star L L plus df, T times df, to Cf star Q plus T times df induces an isomorphism on the E1 page. Okay, I don't know how you count your pages. E1 page of the spectral sequence associated to, why did I say E1? Well, let me just say it like this. Associated to the above filtration. Okay, I'm sorry, Claude, I know I'm not supposed to use the word spectral sequence. You don't have to use the first spectral sequence. You can just say on the associated graded groups. On the graded groups. Okay? Pardon? Okay, well. But this is basic fact. I mean, the map, we said that there is some map here that is defined by multiplication by some Floer-theoretic generator. That Floer-theoretic generator has some action. Okay? That action is much smaller than the gap in actions between the different, the gap in values between the different critical points of x. And the map V also has action much smaller than that. So when you compose them together to get this map, you'll basically still be preserving action. And you can write down an inverse that also has very small action, and then you're basically done. So that's how you prove that that this induces an isomorphism on associated graded. And by the way, when I said at the beginning that Thomas Kragh has a new proof of the result on simple homotopy equivalence, in many cases he can get away without this, but this naturality, which we should think about it, says he can, in general, build a map of E1 pages and see that the E1 pages of some filtrations agree with each other, but it's not always clear that it comes from a chain map, and this tells you why it comes from a chain map. Okay, so once you look at this and you look at the associated group, so if we work over Z pi 1, well, whatever ring we work on, then the associated graded, the homology of the associated graded groups of each associated graded piece is free of rank 1. Okay. So we end up with some map of complexes, and we know that at the level of associated graded is an isomorphism, and the associated graded are of rank 1. And then we'd like to understand what is the torsion of this map. So to compute the torsion of the entire Floer-theoretic map, we just need to compute these are basically some kind of diagonal terms. Okay, so then maybe I should go back to my picture, or maybe it takes a little bit too long to redraw it, so let me just go back to it. So what is involved in computing the torsion of these kind of rank 1 pieces? Well, there is an intersection point between T star Q and Q that lives right here, and there is some possibly complicated complex consisting of intersection points between L and this shift. And there is a map, Floer-theoretic map, obtained by counting some kind of triangles. In fact, you can express them as polygons that look like this. That's what multiplications with U and V look like. Okay. And what you are worried about is the presence of a large path that goes around the space and comes back around. That's what you're worried about. If that was the case, then the map would have possibly non-trivial torsion. But what you work out is that if there were such a path, then the disk would have to do something like this. just basically because of the topology of the space. So by monotonicity, by the monotonicity lemma, such a disk would have to have large energy. So disk with non-trivial contribution to the torsion has large energy. But because of our action estimates, we know that everything has inside has small energy, so this cannot happen. And the precise statement we get is that so the precise statement is that the map on the associated graded is obtained from a map of chain complexes of free abelian groups. Let me just say chain complexes over Z. And by that I mean by tensoring with Z by 1. Okay. So if you have a map of chain complexes over Z, there is no Whitehead torsion. And Whitehead torsion is functorial. So if you can show that things come just by this tensoring procedure, then it would necessarily have to vanish. And then once it vanishes, as I said before, this is just some kind of diagonal, usual trick where if you understand what's going on at diagonal, then you understand everything. And you have to remember that Whitehead torsion had this property that you're allowed to do any off-diagonal transformations you want. Okay, it looks like I have like 5, maybe 6 more minutes. So what I want to do now is just go back and give some idea for how you prove that this map that is obtained by multiplying by the morphisms in Floer cohomology which implement the Floer-theoretic isomorphism, okay, why that has anything to do with the classical map. So, comparison. So for that, I have to redraw that picture. So this is my map. I take a disk. I fix the cross ratios, 4 points. This is just for convenience. We could degenerate it to be 2 triangles, but it makes for a bigger picture. These boundary conditions are on Q. This is my isomorphism from Q to L. I think of this as my input and of this as my output. So this is the map. You just count these disks. So we want to show that you can compare it to the classical map. So what you can do is you can consider, just like in Nick's talk, except in a much, much simpler setting, you can consider disks with boundary on Q, except now they're allowed to have 1 output, and 1 input in which you will put some cycle in T star Q. So you can implement this, for example, you can pick a Morse function H, proper Morse function from T star Q to R, and count configurations. You'll see in a second how ridiculous this is, but let me keep saying it. Count configurations which consist of a flow line from this function, from this critical point down to interior point of a disk, and then you take this disk, and then you have 1 marked point on the boundary of the disk, and that gives you something in Q. Exactly. Good job. So Q is exact. So these disks are constant. So these disks are constant. So you can exactly compute what this map is. And in fact, if you just choose your proper Morse function, if h is just some function on the base, we already picked one, f plus norm p squared, this is just an isomorphism of chain complexes. What that means is that this part of the picture has trivial torsion. Essentially, by definition, there's just nothing happening. There's no non-trivial count that is taking place. And this is the part that we are interested in. So we take something completely trivial, we glue it to the thing we're interested in. And then we do the usual thing, where you glue the node and degenerate to the other side of the boundary of the moduli space. And the other side of the boundary of the moduli space is this. Okay. But we assumed originally that u times v gave us the unit of L. So the count here, is 1. Okay? So the torsion of that map over there, which we defined using Floer theory, is the same as the torsion. So this has same torsion as the original map. But L is exact. Okay, this guy here is just some disk with boundary on L, and then you do some kind of evaluating an interior point of boundary marking, but L is exact. So these disks are constant. And now you just have to go back to what I said at the beginning, where I somehow told you you could compute Whitehead, classical Whitehead torsion using Morse-theoretic methods. So the only thing contributing to this is some kind of Morse flow line. So only Morse flow lines contribute. And that implies it's a classical torsion. And then you can just feed in any of the classical equivalent characterizations of what it means to be a simple homotopy equivalence. Okay, that's the end.